supposed to be? Washed up, pushed out, or on my feet? Tell me, is this a dream, or am I stuck in a movie scene?
Problems. We have resolved every problems at the moment, and we will let you listen to the presentation of Dr. Anothai Thanachareonkit about her window research at Lawrence Berkeley National Laboratory once again. และในลำดับถัดไปนะคะเนื่องจากว่าเราได้แก้ไขนะคะข้อผิดพลาดทางเทคนิคนะคะเรื่องของเสียงเราจะให้ทุกท่านนะคะรับฟังการบรรยายเกี่ยวกับการวิจัยเรื่องหน้าต่างที่ Lawrence Berkeley National Laboratory โดยดร. Anothai Thanachareonkit อีกครั้งค่ะ
Research at the Berkeley Lab. You may have heard about Lowy windows and electrochromic windows. These are the examples of the technologies that Window Group at Berkeley Lab has been working on for decades. You may also use the Radiance program, Comfen or Resfen software for lighting simulation and energy analysis. These are a few examples of the software our group developed. In this talk, I will give an overview of our past research, as well as what we are working on now and how you could connect with our team. I will start with a brief description of myself. At Berkeley Lab, my work includes the assessment of daylighting performance of Windows technologies, visual comfort, human factors studies, and energy analysis that are related to the windows. A few examples of my works are studies of daylight redirecting film and automated light redirecting system. I'm also working on the audit side, for example, working with the U.S. Environmental Protection Agency or U.S. EPA on Energy Star for window analysis. I started working on window and daylighting research at the Swiss Federal Institute of Technology in Lausanne, Switzerland. Before that, I studied architecture and building technologies at the Faculty of Architecture, Chulalongkorn University in Bangkok. Shortly after I finished my dissertation in Switzerland, I went back to Thailand and was teaching the environmental design classes for the INDA program at Chulalongkorn University for a year. Then I went to California Lighting Technology Centers, CLTC, as a postdoc researcher and moved to Berkeley Lab in 2011. In Berkeley Lab, I'm working on window research in window and envelope group until today. Prior to the overview of the window research at the Berkeley Lab, I would like to give a brief introduction of who we are. Berkeley Lab, or LBNL, is the short name of Lawrence Berkeley National Laboratory. Berkeley Lab is one of the 17 national lab systems supported by the U.S. Department of Energy and is managed by the University of California and is charged with conducting unclassified research across a wide range of scientific disciplines. Berkeley Lab was founded in 1931, so this year is our 90 years anniversary. 14 Nobel Prizes are associated with Berkeley Lab. Technologies developed at Berkeley Lab have generated billions of dollars in revenues and thousands of jobs, saving as a result of Berkeley Lab development in energy efficient technologies from cool roof to window coating to appliance. At Windows and Envelope Group, we support the mission of the Department of Energy to increase the energy efficiency of windows and buildings. We accomplished this using advanced technology development, algorithms, and software tools, supported by our testing facilities and experienced scientists. In our team, we are a multidisciplinary group. We have researchers with different backgrounds, architects, engineers, physicists, scientists, programmers, and more. As I mentioned in the previous slides, our group has been working on window research for 50 years. In this talk, I have selected a few highlights of past and ongoing research, including the facilities, softwares, and outreaches. The past research will be an overview of low-E windows and electrochromic technologies. I will talk about the ongoing research highlights: high-performance insulating windows, BSDF validation, and window films. In the last section, I would like to present to you the recent outreach work on window videos and Energy Star for Windows. The Windows and Envelope Group has facilities for measurement of window elements on scale ranging from full scale test bed for anode testing to the lab instrument for analysis of the thermal and optical properties of individual elements of the products being studied. We also have a mobile instrument for field measurements. Today, we are still working on research and development of our facilities and instrumentations. The first facility I would like to mention is the LBNL window test bed facilities. These outdoor test facilities contains 3 thermally isolated chambers that have been instrumented to measure thermal, daylighting, and occupant impact of advanced window technologies. In this setup, you see in the pictures, the 2 test rooms on the left had the light redirection films installed and compared to the reference test room on the right. This facility allows us to compare 3 different technologies within the identical thermal and lighting ambience under the real sky condition. In this test, the lighting energy, daylight availability, and visual comfort were evaluated. The 3 cells in the facility have the interchangeable south-facing facade, interchangeable exterior and interior shading devices. They were equipped with the power metering for HVAC lighting, net window heat flow measurement, photometric capture throughout the room with SDR imaging, weather station, outdoor and indoor video monitoring, and sky camera that could capture sky luminance mapping. In this slide is the mobile window thermal test facility, or we simply call it MOVIT. MOVIT is a calorimetric measurement facility for measuring thermal and solar performance of windows. It allows for accurate measurement of the time varying flow of energy through windows under realistic field conditions. The measurement facility consists of a pair of outdoor room size calorimeters, which measure the net energy flow through window samples in side-by-side tests using ambient weather conditions. The two calorimeters are housed in a measurement trailer seen in the pictures. MOVIT has had an important role in the field testing of low-E windows and high insulating performance windows. So in these pictures are the instruments at the Solar Optical Property Laboratories, or I will call it shortly Optical Lab. The Optical Lab has a complete set of instruments designed to characterize the detailed radiometric and optical properties of window glazing and shading materials. I will go very fast in this slide, but please feel free to contact me for further details if you're interested. Number one on the top left is the spectrophotometer used in the glazing industry to measure reflectance and transmittance in the solar range. The second one, number 2, is the large goniometer. This instrument was designed and built by PAP Advanced Technologies. It is located in a dark room. This goniometer is able to span the full solar spectrum with high speed, precision, and angular resolution for any possible angle of incidence. This goniometer measures the complete ongoing bidirectional scattering distribution function, or BSDF, of a material. Number 3 is also the spectrogoniometer. It was built to LBNL specifications to measure specular transmittance and reflectance versus angle of incidence of specular samples. Next instrument is the large diameter integrating sphere. We also have a smaller one, not in the photos. It measures total visible transmittance of complex light redirecting, diffusing samples with large-scale non-uniformities. Number 5 is the ellipsometer. It is a powerful tool for determining the optical indices and thicknesses of the layers in the thin film coatings. Number 6 is the emisometer. It measures hemispherical thermal emissivity of opaque samples. The last one is the FTIR spectrometer, measure transmittance and reflectance in the wavelength range from 2.5 to 44 microns. The optical lab plays an important role in measurement of the spectral and spatial light scattering properties of glazing, shading, and daylighting materials and systems. More information about the lab is available on the window website. The next lab I would like to introduce is the infrared thermography laboratory, or IR lab. IR lab focuses on characterization of heat transfer through window and framing system using measurements combined with high-resolution infrared thermography imaging of sample placed within a controlled environmental chamber. Prototype improvements are made through visualization and analysis of localized surface heat transfer around edges, spaces, and other connection between surfaces of highly insulating window and framing systems. Quantitative data are used to understand complex heat flows and to validate finite element heat and fluid flow numeric models. Beside the window and envelope groups facility I have mentioned earlier, Berkeley Lab also has the first test bed in the world that can evaluate the energy efficiency of major building systems as an integrated system under real-world conditions. Flex Lab, or facility for low energy experiments in buildings, is the most adaptable, comprehensive, and advanced building efficiency testing facilities. Flex Lab test bed can monitor and access HVAC, lighting, windows, building envelope control system, and plug loads in any combination within the 8 side-by-side test cells that include 2 rotating cells. Several window research projects have been tested in Flex Lab. Right now, two window film projects are being tested in 5 cells. And we move to the next interaction on the software, on the Windows software. Berkeley Lab Windows software tools were used for design and development of energy efficient window technologies. These tools are moving the window industry and research toward virtual, rapid product design and product development, which accelerates design to market delivery. The diagram shown here illustrates how the Windows software tools are used in each step of the evaluation process. I would like to start with the number 5, the one in the center, the Berkeley Lab Windows software. Berkeley Lab Window is a publicly available computer program for calculating total window thermal performance indices, U values, solar heat gain coefficients, shading coefficients, and visible transmittances. The program can be used to design and develop new products, to assist educators in teaching heat transfer through windows, and to help public officials in developing building energy codes. Berkeley Lab Windows has a close relationship with the other databases and programs. I will give a very brief description of this program. More details and the instruction could be found in the Windows website listed here, the windows.abl.gov/software. The first one, IGDB, or the International Glazing Database, is a collection of optical data for glazing products. Spectral transmittance and reflectance is measured in a spectrophotometers and contributed to the IGDB by the manufacturer of the glazing products. The IGDB is part of the download package with Berkeley Lab Windows. So when you download number 5, you get you have the number 1 in it. The optics computers program is designed for work with optical data for glass and glazing layers. Integration with the IGDB makes it easy to build stacks of multiple glass layers and calculate the resulting optical properties. Basically, you can design your own glass layer using optics to have the using the database from IGDB in optics, and have your own windows for the analysis in the Berkeley Lab window program, window software. The next software is Term. TERM is a program developed for use by building component manufacturers, engineers, educators, students, architects, and others interested in heat transfer. Using TERM, you can model two-dimensional heat transfer effects in building components such as windows, wall, foundation, roofs, and door, appliances, and other products where thermal breaches are of concern. TERM's heat transfer analysis allow you to evaluate the product's energy efficiency and local temperature patterns, which may relate directly to problems with condensation, moisture damage, and structural integrity. The CGDB is a new optical properties database for optically scattering system or complex system. For example, shading device and materials such as Venetian bright, solar shade, drape, cellular shade fabrics. The light redirecting materials, for example, prismatic films. And scattering glazing like diffuse glass, glazing frit, decorative glass. This database is similar in nature of the IGDB. The number one. The calculated data from Berkeley Lab Windows software could be used in many design tools. For example, in Radiance, Confen, Resven, or Energy Plus. Radiance is used in Windows software tools for the calculation of optical properties of optically complex window products. Confen is a tool designed to support the systematic evaluation of alternative fenestration system for project-specific commercial building applications. Thus, when calculates the energy and cost implication of the window compared to an insulated wall, the relative energy and cost impacts of two different windows can be also compared. Yeah, it's a good one. Okay. The next one, I would like to talk a little more about Radiance lighting simulation because it is such a powerful program in window research. Radiance is a series of programs for the analysis and visualization of lighting in design. It employs advanced ray tracing with optimization for complex building geometries and fenestration systems. The user can input files, specify the scene geometry, materials, luminaire, time, date, and sky condition for daylighting calculation. Calculated value includes spectral radiance, for example, luminance and color, irradiance, such as luminance and color, and glare indices. Simulation results may be displayed as color images, numerical value, and contour plots. Radiance is used by architects and engineers to predict illumination, visual quality, and appearance of innovative design spaces, and by researchers to evaluate new lighting and daylighting technologies. The pictures here show like how the Radiance could render the lighting scene, and below is how the Radiance technique and how we assign the material of the fenestration system would have an impact on how the lighting simulation. Radiance is also used for rendering rooms in many other softwares, like what you see here, like Confen, Dialplus, Honeybee, Diva for Rhino, and many more. In section 2 is the overview of low E windows and electrochromics technologies. We start with the low E windows. Berkeley Lab has developed the low emissivity or low E window coatings with the industry for over 5 decades. Low E coatings had been around before in specialty application like oven windows. Starting in the 70s, Berkeley Lab and industry investigated how this technology could be used to make building windows more efficient. In the 80s, Berkeley Lab collaborated with the startup Suntech on developing a transparent film that was installed between the panes of a multi-pane windows. This first commercial low-E products was introduced to the market in 1981 to demonstrate the window effectiveness in different climates. Berkeley Lab created the MOVIT, the Mobile Window Thermal Test Facility, as I mentioned earlier. And by 1988, 20% of all windows sold in the US had a low-E coating. In the 1990s, Berkeley Lab helped create low-E coating targeted at different climates, a soft coating that blocks nearly all infrared light, ideal for warmer climates, and a hard coating that allows some of the sun's shortwave infrared light to pass through and is ideal for cold climates. In the year 2000, Berkeley Lab continued to develop window term and the associated window component databases in order to develop new codes and ratings. Now the low-E windows becomes the industry standard and incentive innovation. Another highlight that I want to point out is the research and development of the electrochromic or EC window. Electrochromic windows provide a light control solution aiming to avoid too much light along with associated glare and excessive heat to enter the space. EC windows change transmission properties in order to control over the amount of daylight and heat passing through the window while still allowing a transparent view through the tinted glass. What you could see here is could change the tinted level and we can still see the outside. Window and envelope group has contributed to electrochromics technology since the 1970s. It first adapted the thin film EC for Windows in 1980 and applies to the last window in 1989. Several evaluations, such as modeling of economic benefits, visual impact of EC, field study, full-scale testing, and large-scale field demonstration were done by Berkeley over the past years. More than 100 papers related to EC technologies were published between 1973 and 2018. In section 3, the high performance isolating windows, BSDF validation, and window film testing will be presented. The first one is the high, I want to talk about is the high performance insulating windows, or I will call it the high-R windows. In the United States, particularly in the cold climate, windows present a higher heat loss compared to the other building elements. Here you see windows provide like 47% heat loss compared to what to roof, walls, and floor that have lower. The current strategies to reduce this heat loss through windows are triple or more glazing or suspended film which are costly and heavy. High performance insulating windows or higher windows was studied to solve this problem. The project goal is to assist development and adoption of high performance windows by focusing on the development of alternative center glazing layers for multiple low-E gas fuel units. Our aim is to increase the number of technological options available to industry for center glazing layers. The two options in use today, suspended film and triple glazes glass unit with low emissivity coatings and insulating gas fields, are technologies that have been in use for over 2 decades. Using lightweight, thin, non-structural layers, the focus of this project offers several potential manufacturing and performance advantages. This slide is an example of the thin triple windows development. To avoid too heavy, too wide, too expensive, and long return of investment in triple pane windows, the thin triple was developed to have a single piece spacer is possible, reducing labor and material costs and potential for gas fuel leakage. No significant weight change over industry standard double pane unit. And also minimal or no change in standard operating hardware. Thinner center layers allow products to fit in existing cross sections, reducing the need for revised framing systems. Pressure equalization between the internal gaps is possible, reducing potential glass deflection. Currently, this technology has been demonstrated in many US locations and hopefully can be widely used within the next few years. The next ongoing highlight is the BSDF validation. As some people may know, but anyway, I would like to give a short definition of the BSDF again. BSDF, or bidirectional scattering distribution function, describe the directional transmission and reflection for many different combinations of ongoing and outgoing direction. As you can see in the light pictures, when incident light beam reach a surface, the reflected scatter distribution is called BRDF, or bidirectional reflecting distribution function, and the transmitted scatter distribution is the BTDF, or bidirectional transmitting distribution function. A BSDF is the combination of ingoing and outgoing direction of incident light. In lighting simulation, an accurate BSDF measurement means also a more accurate lighting and energy analysis results. For a simple window, BSDF measuring is more straightforward than for a complex fenestration system, or CFS. Therefore, this project, the BSDF validation, is aiming to develop and validate the methods and model for characterizing BSDFs. How to make it is by first develop and test protocol for measuring the scattering property of CFS, or complex fenestration system. Next is develop and validate model for generating complete BSDF datasets from measurement, quantify margin of errors. Develop and validate method for using BSDF datasets in simulation. The next step is develop the low-cost methods for BSDF generation in collaboration with industry. Develop and also develop required shading and daylighting product database, and also assist industry in the development and establishment of technical document and rating procedures. One of the approaches to achieve the goal is the field testing. The solar and optical performance of the window system was measured in the full-scale test bed. The distribution and intensity of transmitted flux was verified using HDR imaging techniques. HDR cameras. Here we can see with the difference between the simulation from radiance and the measurement of the windows using the HDR cameras. We are working on identification of source of errors across the BSDF data preparation pipeline for the simulation. And the next project I would like to introduce one is the window film. Currently, Berkeley Lab is working on two separate CEC, California Energy Commission funded projects on window film. We are now testing window films in 5 cells at Flex Lab. In one project, we are testing commercially available films. In the other one, we are testing prototypes for a window film startup. The goal of these two projects is to evaluate the benefit of window film in commercial buildings, energy savings, payback, and human comfort and health, and assist the window film design development. The last section I would like to talk is to mention is the outreach. I would like to introduce the two recent outreach projects created by our groups. The first one is the window videos. Window and envelope group at Berkeley Lab have several outreach projects. Recently, we have launched a series of window videos on energy efficiency and window basics. I have to say I enjoy watching it and believe it will help the public understand the terminologies, basic of windows. I could give you I should point out that you can find the windows abl.gov/windows-videos. The website would be like this, and you will have the different series. The first one would be like the basic of windows, and then about the heat flow and solar radiation, the optical properties of windows, for example. And the last slide, I would like to give you an overview of the new version of Energy Star for Windows that Berkeley Lab is working within the U.S. environment with the U.S. Environmental Protection Agency, or U.S. EPA, similar to the appliance like refrigerators or the AC unit. Windows has also Energy Star ratings. The benefits of Energy Star qualified windows are the lower energy bills, more comfortable, and protect your variables. Berkeley Lab have recently worked with the US EPA on energy analysis, return of investment and payback period for the new Energy Star for Windows version 7. And thank you very much for participating. Please feel free to ask any question during the Q&A session or later by emails. If I can't give the good answer at the moment, I will do my best to find them out and get back to you later. Thank you.
And that is the presentation from Dr. Anothai Thanachareonkit. She was telling us about her window research at Lawrence Berkeley National Laboratory. And next, our next guest speaker will be telling us about how to pave the way towards a sustainable living with bio-based and renewable materials. Our next guest speaker is a professor, an associate professor, Dr. Supakij Suttiruengwong. He is currently working as a professor at the Department of Material Science and Engineering, the Faculty of Engineering and Industrial Technology at Silapakon University. ในลำดับถัดไปนะคะขอเรียนเชิญรองศาสตราจารย์ดร.สุภกิจสุทธิเรืองวงศ์ค่ะจะมาเล่าให้พวกเราฟังนะคะสู่การก้าวไปสู่การใช้ชีวิตอย่างยั่งยืนนะคะโดยใช้วัสดุชีวภาพและวัสดุที่สามารถหมุนเวียนได้ค่ะกราบเรียนเชิญรองศาสตราจารย์ดร.สุภกิจสุทธิเรืองวงศ์ค่ะ
So today, can you hear me? Yes. So I start again. Yeah. First of all, I'd like to thank the organizing committee for inviting me to this conference. Also, today I will share with you some of my view on the sustainable development in terms of materials, material engineering, material science, and also how to prevent this climate change in terms of using the materials. Just a little bit of my background. So I actually, as you may know, Silapakon University has 4 locations, and two in Bangkok, including President Office, and one in Nonthaburi and another one in Phetchaburi. My workplace is in Nakhon Pathom. That is on the left of the Bangkok. So you can go to the west around 1 hour by car, and then you will reach Nakhon Pathom. So I'm working at the engineering faculty. I actually graduated from Germany, so I can speak German, I can speak English. So I had my master in England, in Wales. And so now I published more than 49, actually now it's more than 49 publications. And I'm working generally with many partners and collaborations. Basically, I work with the most of the biodegradable and renewable materials. In our group, we focus on social development goal number 12. So we are looking at the possibility to produce and look at the consumption of the bio-based and biomaterials in terms of industry production and also promotions. In our group, we focus in many different material processings and also some new materials in terms of natural and bio-based, bio-derived materials. So in this slide, you see our specialists. We look at the beginning, we looked only the materials. Now we look at the whole value chains. So because if you want to understand the climate change, you have to understand the carbon footprint. But if you want to understand the carbon footprint, you have to calculate for the whole value chain, depending on how much data we have. But at the moment, we are working closely with many companies and also collaborations, because if you want to do this whole calculation, you need a lot of partners and also collaborators. We also have lots of products involving circularity, circular economies, bioeconomy and green economy in Thailand. So we are developing most of them basically plastics from natural fiber, from bio-based and natural renewable materials. So we develop mostly of the most of the things for the household use and also industrial usage. So in many cases, we also look at the things that we will be talking today. So the content of my talk is we will focus on what's happening at the moment and how about the renewable materials, how renewable material can be alternative to our daily life. And also I will show you some of my research topics and also the finding. And finally, I will summarize what we find today. So if you look at the moment, we have COP26 going on. And when you look at the fact that COP, the climate change conference in UN, and they always talk about how to reduce the temperature even less than 1.5 degrees centigrade. But at this pace, we are looking at how to sustain the 1.5 degree. With how can we prevent it not to increase this temperature to more than 1.5 degrees centigrade. So the goal is to decrease the carbon dioxide emissions by 2 gigatons or the 2 billion grams per year, which is very difficult. However, this is possible, but I think if you ask the scientists, it's very difficult to do this because you need a lot of collaborations and also politics. So when we look at the report here, 10 new insights in climate science 2021, so it's available online, you can download it. What it's involved, the material most is key finding number 6. Key finding number 6 is very interesting. They look at this how to support the household behavioral change. So-called how to make the lifestyles 1.6 degrees centigrade lifestyle. So the panel, so the scientific panel, try to set the standard for the consumption corridors. That means every day we are over consume using many things that we don't need. For example, we use a lot of electricities. We eat more food, or we order more food, but we eat less. So, and also we are looking at the options. How do we behave in terms of transportations and also in terms of the lifestyles. If you look at the mobility, so in the future, I think it's very exciting to have the EV car. and it's accelerates very fast at the moment. So they are looking at the carbon footprint using mobility, for example, car transportation. At least we have 72% overconsumption. So that means we can reduce this. Is the best way to reduce this consumption is to use the EV car. But again, when we talk about EV car, we have to look at how this electricity come from. So it should come from renewable energy as well. So in terms of food, so they think that we have to look at the footprint for reduction in terms of nutrition. So they think in developed countries, they consume at least 47% more. So they can reduce this if we look at carefully about the carbon footprint for the foods. For the housing, it's very straightforward. In developing countries, they use probably 68% overconsumption in terms of footprint. So in this case, it means that the housing in developed country, they use more energy. So you have to go back to the design of the building. You have to go back to the material used in the building. You have to go to the embodied carbon and also operational carbon, which I will talk about this in the next slide. So if you look at the materials in terms of the greenhouse gas emission, you can see on this slide, the total emission is above probably 50 gigatons CO2 per year. So CO2e means CO2 equivalent. So if we talk about greenhouse gas, you can have also methane gases, and also you can have nitrous oxide. These two gases are now is very important because even though the two gases that I just mentioned, they emitted very low, but the problem is they have very high greenhouse warming potential. So now I think UN and many scientists are looking at methane gases and also nitrous oxide as well. So in terms of CO2, you can see on this slide, if you look at the graph here, for the iron and steel production and cement, also lime, and also plaster, rubber, and plastic. These kind of materials emit most CO2 or the greenhouse gas in terms of productions, and also compare to the other materials such as paper, aluminum, wood, and also pulp. Yeah. So to set the scene here, we have to look at the material for the in terms of construction. You have iron, you have steel, and also you have the cement. And in terms of decoration, and in terms of a household and daily life materials, we have plastic and rubber. So including to these two categories, you have already produced a lot of CO2 emissions compared to the rest. How about what affect most in terms of the production? From the slide, you can see on the first pictures, the material production contributes more CO2 emissions, and also the energy supply in terms of production as well. For the material extraction or mining, this consume less, or this produce less CO2 emission. However, if you look at the plastic, the types of material, you can see here the iron, steel, and also cement and plastic, rubber. These three materials emit more than half of the CO2 compared to the other materials together. On the other hand, if you look at the sectors, the sector of the materials, you can see the constructions. Constructions emits more than almost 50% of the CO2. So On the other hand, you can have like machinery, metal products, and also final use. They also produce the CO2 and they emit it to the rest of CO2 usage. Another problem that we are facing at the moment is the end of life of the materials. For example, plastic. Most of the plastic end up in the sea. And as you know, we are in Thailand as well. We are amongst the most polluted plastic into the sea. We also leach the plastic into the sea because we have the mismanaged and also the overconsumed plastic in Thailand. So it is predicted by the Ellen MacArthur Foundation that in 2040 you will have the two times more plastic use, and also we will have the 3 times more plastic going into the oceans. When you talk about 3 times, means 3 times of the plastic waste. So, and you can have a 4 times plastic stock in the ocean. That means the plastic in the ocean is the last destination for the waste. So if you have more plastic waste, then you can expect the more plastic accumulation in the ocean. And by 2050, you can have the plastic more than fish. So what plastic does in the sea? Normally, we have 3 categories of plastic, starting from the macroplastic. Macroplastic, we can always see them. For example, plastic bags, utensils, or whatever that you are, many products that use in our life, that we can call that macroplastic. And after the plastic being disposed or being managed or mismanaged, whatever, they will break down into small pieces. So we can call this microplastic. The definition of microplastic is defined as the plastic that's less than 5 millimeters and to, I don't know, to maybe 1 micrometers. And now you can have a nanoplastic. It's not possible for us to see nanoplastic. So this is how important it is in the future that we can track down this nanoplastic, because we don't know yet what is the impact or what is the dangerous of this plastic in terms of food chain. And this plastic can go into the food chain through the environment to the oceans, and then it's going to the food chain and together with some toxic chemicals, and then at the end they will come back to the human. So in our lab, we also looking at this option for the plastic as well. So if you look at the data here, this data collected during the COVID-19 pandemic, and it was published recently, and this data collected from 41 countries with 202 participants. You can see on the red graphic, there are increase in the single-use mask. This is a face mask that also come from plastics. So it's, and also you have the food packaging. This is not surprising, because this is probably originated from food delivery. And also you can have the single-use plastic bag and film and bottle, and also cutlery. On the other hand, you can have plastic straw and rigid plastic packaging, but the consumption of these two straw and rigid packaging stay very low. So there will be trend about increasing in plastic packaging. So that means if the government can manage and organize the way the plastic goes, it will be very useful and also very important for the plastic pollution not to have an effect on our daily life. So on the other hand, with the pace of the material science and engineering, we expect more new technologies coming. For example, you can have the robot with a face recognition. Most of the robot, they also produced by steel or metal or even plastic, and also the electrical circuits, they also produce in the plastic and also some rare materials, which is very important for the CO2 emissions. For the space station also, they also try to recycle the plastic using the 3D printing technology. So this printing technology can produce probably less CO2 emissions in terms of they produce new plastic out of the old one. So we call that recycle, on-site recycled. And also the expectation of the EV car, we can have more plastic. And this plastic are relatively new and also designed for the EV car. And if you look at the plastic in such a new technology, you can have the new plastic with the low carbon emission as well. So they have to take this into account in terms of producing the vehicle, which is very important for the transportation with the low emission of the CO2. How about the renewable materials? How they fit in? When we look at the research, recently, I just look at the keywords following the embodied carbon, operational carbon, and also I look at the net zero build materials. I also search for the renewable materials. You can see here from the 2012, the trend of researching renewable and embodied carbon, operational carbon, and also renewable material seem increasing. And especially in terms of built environment and renewable materials, there are almost 100 publications in 2021, but in 2022 it's not yet reported, but some of them already in place or prepared already for publish. And if you look at the material in terms of renewability and sustainability, we have to look at one important point. That is the tracking of the carbon and water consumptions. So we can call this life cycle assessment or whatever you call it. Somebody will look at the carbon footprint, water footprint. But on the other hand, if you look at this in terms of engineering, we can find the life cycle of each service and products. So for some of the service and products, it depends on what we are looking at or what information we can gather and what information can we calculate in terms of CO2 emissions. So we have to track this carbon through the life cycle. For example, you can have the options from the cradle to gate. You can have the option from cradle to grave, and also very difficult but worth doing one is the cradle to cradle LCA. In terms of our lab, we are looking at the materials and energy flow for some processes, depending on the data that we can obtain. For example, we look at the materials from the starting point to the end of the productions. And we can also follow this into the end of life. For example, go to the consumer and then go back to the materials flow back to the manufacturer, or even go to the landfill or incinerations. So if we look at the carbon, this life cycle of the carbon, we also can compare it with the built environments in terms of the embodied and operational carbon. So if we can calculate this whole embodied and operational carbon, we can also predict the emission of whole life cycle of the building and also the emission during the the usage of the building. For example, during the whole process that we construct the building, we call this carbon is embodied carbon. And during the housing phase and during the using phase, you can have the operational carbon. So when we stay in the house, so we use a lot of the energy, and that's it. The operational carbon can be calculated through the energy efficiency and energy emitted through the carbon emissions. But for the operational carbon, it's very easy. I think it's very easy to prevent this because you can have renewable fit-ins. For example, the solar cells, as for example. On the other hand, what I would like to point out is normally when you talk about build the environment, we don't talk about what's going on during the period of usage or the residential period. So in this case, you can have many emissions, carbon emissions from the durable products and also from the single-use item that's being used by the owner or the landlord. So this can be associated with a carbon living. So if you can track down the durable products and single-use item in the house and during the residential period, then we can also add that into the operational carbon, and then we can have the total or the net carbon emission during the time or during the age of the residential period. So in COP26, as I mentioned, they also have the model house. They call it an embodied carbon exemplar. So if you can see here that most of in the house is consisted of the timber-based materials. So they use a lot of timber. So this timber store a lot of carbon. So you can call it a biogenic carbon. So that means you already have this carbon storage. So after you calculate the whole carbon emission for the whole process, constructions, transportation, site energy, and waste, so you can reduce a lot of carbon, embodied carbon in the house as well. However, construction, such of things, you also have to look at the probably window technology, heat transfer technology, and also many different technology should be also involved in terms of calculation for the energy efficiency as well. And for the materials, we have two options. When you look at this slide, you can have it on the left is the biological cycles, and on the right hand side is a blue color. That is the finite materials. So for the two cycle, it is inevitable to choose one of the cycle. Probably we can have both cycle at the same time, but both of the cycle have different options. For example, if you look at the green cycle stand for the biological cycle. That means you can have the bio-based or natural materials that come into the manufacturer, and you can produce some of the bio-based products out of the bio-based and natural renewable resources. However, depending on the usage on the applications, it is not possible that you can always use the natural fiber. It's not possible that you can always use the natural renewable resources. Some of the part you may need to use the, for example, metal, steel, and also lime. So this kind of thing maybe it's not possible that can be substituted by the biological cycle. So you can have also both at the same time. But on the other hand, if you can use more clean cycle, you can reduce more CO2 emission as well. At the moment, we have also, there is a demonstration for this kind of business. For example, you have a new circular business model. You can also return the old furniture to the company, and the company will sell that will sell this furniture for you. This is another model. There also another demonstration in Thailand. They use a lot of wastes produced by their business, and they put it back into their shop, and they call this upcycle and recycling demonstration circularity. On the other hand, for the operational, they have many renewable materials involved. For example, hot cup, cold cup, straw, and also paper bags. They also use low impact and low emission carbon in terms of the operational as well. And with that, I would like to also to just a little bit precise on renewable and renewable materials and biomaterials. What does it mean in terms of the materials? How it affects the CO2 emissions? When we talk about biomaterials, we talk about the materials that come from the nature and also renewable. For example, plant-based material. It can extract in terms of chemicals as well. It does not need to be only the material, raw material itself, but we can also extract some chemicals out of it and use it as well. So this we call renewable bio-based materials. And if we look at the CO2 footprints or the carbon footprints, we can see that if we use the natural fiber, natural materials, the CO2 or the greenhouse gas emission is very low compared to the glass fiber, compared to the carbon fiber, which is very high CO2 emission because they are synthetic fiber. They come from the fossil fuel and fossil materials. And in terms of plastic, we can have many different kinds of plastic. For example, in our group, we are working on the bioplastic. So this bioplastic can derive from two types of materials. One is the bio-based, as I mentioned, and another one is biodegradable materials. So when we talk about biodegradable material, we have to talk about the standards as well, because everything in the world is biodegradable, depending on the period of time. So it doesn't mean that something is biodegradable in 1,000 years, in 100 years. No. In terms of bioplastic, we are looking at the standards as well. If we talk about biodegradable plastic, we are talking about the compostable plastic. So we have a standard. This plastic can compost in terms of industrial compost only in 90 days. And you can have only very low emissions to the air for the CO2 emission. So in our group, we looking at the whole value chain of the biodegradable and bio-based plastic from the feedstock until the end of life. So at the beginning, we had only to develop some research in the field of the conversion technique and technology for the processing, especially plastics. And now we look at the options of the end of life as well. Just to give you some example of my talk, we had also evaluated some single-use item in terms of the carbon footprint. This was published 7 years ago. We compared the straw, bio-based straw plastic with the PP or the polypropylene or conventional petroleum-based straw plastic. And we also look at for the whole process from the production until the end of life of the process. And we also have the calculation of the carbon footprint, the activity involved in the CO2 emission. And we can conclude that using the bio-based straw, you can reduce the GHG or the greenhouse gas emissions by almost 1 kilogram CO2 equivalent per 1 kilograms. So after that, my student also found a company we call a startup company. The company called the Smart Bioplastic, and they are still learning and they are still developing some idea. So we have also this life cycle analysis for the process in the company. And we look at the whole process from the transportation of the materials and to the delivery of customer products. And we also look at the end of life option, many different options. For example, we can put the plastic compostability at home. And also we have to look at the end of life of plastic in the ocean as well. For example, we look at the end of life of option in the mangrove condition and also open sea water. So we working closely with many partners, as you can see here. So in terms of the end of life, we also working with some industrial company, and also we also working with the government, DMCR as well. Just to conclude my talk, I just introduced you some of the idea that the carbon emissions from some materials that we are using at the moment is very high, and if we want to we want to stop the products that have a lot of GHG emission, it can cost a lot of money. Also, it can also cost a lot of technology as well. In terms of materials, there's a trend towards the renewable, and also it's not possible that we can work alone. We have to collaborate, yeah? Because it will go across the value chains and it involves a lot of partners and players and stakeholders. So we have to look at many different fields as well. In terms of the embodied and operational carbon, they are key to the new design, but also the real key to the new design is not only the process, but also the materials. You have to look at the new materials. We have to look at the many different heat transfer and also energy efficiency materials. For the lifestyle as an alternative, I just finish up with my products and my research as a potential that if we are using this kind of stuff, for example, renewable and bio-based materials, we can also emit very less carbon. It's, for example, straw. We can, if we use 1 kilogram of the straw products based on the bio-based materials, we can emit less than 1 kilogram as well. That's it. And I thank you very much for your kind attention. Thank you.
Thank you very much, Associate Professor Dr. Supakij Suttiruengwong, for sharing with us how we can live our life towards a more sustainable living with bio-based and renewable materials. กราบขอบพระคุณนะคะรองศาสตราจารย์ดร.สุภกิจ สุทธิเรืองวงศ์ค่ะที่มาแนะนำพวกเรานะคะสู่การใช้ชีวิตนะคะโดยที่คำนึงถึงสิ่งแวดล้อมมากขึ้นนะคะไม่ว่าจะเป็นการเลือกใช้วัสดุที่สามารถย่อยสลายได้ตามธรรมชาตินะคะหรือว่า bio-based material ต่างๆมากมายค่ะกราบขอบพระคุณอาจารย์มากค่ะในลำดับถัดไปนะคะเราก็จะมารับฟังการบรรยายนะคะจะเป็นเรื่องของปัจจัยท้องถิ่นนะคะของประสิทธิภาพการสร้างเมืองในแถบเอเชียเขตร้อนนะคะในวันนี้เราได้รับเกียรติจากรองศาสตราจารย์มัซายุกิอิชิโนเซะนะคะจาก Tokyo Metropolitan University ค่ะAnd next, I would like to invite our guest speaker who will be telling us about local factors of urban building performance in tropic Asia. Ladies and gentlemen, please join me in welcoming Associate Professor Masayuki Ichinose from Tokyo Metropolitan University.
My name is Masayuki Ichinose from Tokyo Metropolitan University. First of all, I'd like to thank to invite me this conference this time. And my presentation is talking about sustainable building, especially focusing on the tropic Asian countries and cities. So, I would like to talk about myself. First of all, I'm now working for Tokyo Metropolitan University. This is a public university organized by metropolitan government. And my department is architecture and building engineering. It means we are educating architectural design and the building engineering at the same time. For the international activity, I'm working for ASHRAE for 6 years, and I'm belonging to the Japan chapter, and I was awarded first place of technology award 4 years ago. My research area is building mechanical engineering, especially focusing on the air conditioning system. And I also study on the facade engineering, UHA study, beam FM, etc. So today I'm talking about 4 topics. First, just talking about introduction. I'm not sure today's audience is building engineering area or architecture design or general people. Anyway, I'm talking about my research background and the presentation introduction. Followed by actual performance survey. I'm now doing the research survey in Pacific Asia for a few years, talking about this topic, followed by possible solutions, just ongoing ideas and some test cases right now. And finally, I'm asking you some possible further collaboration with you. First, I'm talking about introduction. As you may know, before we are going to the zero carbon, anyway, we are still now increasing our energy right now. One of the problem is Asia, including Thailand, Japan. We are now occupying maximum energy all over the world in region. Some statistics says by 2030, Asia accounts for 50% of energy consumption all over the world. So we are very responsible for the sustainable of our Earth right now. And other statistics also say the potential of energy conservation is quite high. India and China, of course, very large potential, but including Thailand, Asian countries has also big potential compared to any other Asian country, Japan. So this is why I'm now doing the tropic Asian countries building survey. This is also very famous statistics from IPCC fourth report. This is a comparison of CO2 mitigation potential by 2030. It is a little bit old already, but very clear situation of our building area is how much we have mitigation potential for the CO2 and GHG. This is kind of estimation, different cost range for the CO2 mitigation cost range. Anyway, our area is any cost range, we have big potential compared to any other industry. So in any other words, it means we building area didn't do anything at this moment about sustainability. So this is very very clear situation of Asian countries building, what happened. This is located in central Bangkok. The building is located in Singapore, Jakarta, Hong Kong, Kuala Lumpur. Anyway, buildings nowadays becoming like a big shape, and almost building facade is grass grazing, only grazing. And the fully air conditioned inside building, it means energy consumption is huge. So from 2015, I decided to on-site investigation this kind of building, how much energy is consumed, and how we have to do for this kind of buildings. And yeah, so I started this on-site survey research project. Of course, we are doing in Tokyo, and from Taipei, Hong Kong, Hanoi, Bangkok, Singapore, Jakarta, with this collaboration university, we do the on-site survey. Target building is like a super high-rise and grass building, looking energy consumed buildings. This is an example of our workshop in central Bangkok 2 years ago, before COVID-19. We do this kind of workshop, student workshop, and the survey at the same time. This workshop is organized in Suttiruengwong University. There are Suttiruengwong University students, our Tokyo Metropolitan University students. They do collaborate measuring devices survey all together, and doing the summarize the data, and make a presentation. And our professor is going to was going to critique and give a comment like that. I really would like to restart this kind of workshop again. So next, I'm talking about actual performance survey. This is a summary of our research projects. This is a target building sample photos in tropic countries these few years. As you can see here, the GFA of the building scale is quite big. The minimum is around 10,000. The maximum is more than 200,000 meters square. So the target building, target office, mainly we are just doing the survey on the office spaces. And the target office area is 1,000 or a few hundred meters square, like that. We already do this kind of survey, almost 30 something buildings. Of course, there are also a lot of target building in central Bangkok. This is a very simple answer. What happened inside building such kind of super high-rise building in tropic area? This graph shows the operative temperature distribution during office hour in Jakarta, Hong Kong, Singapore, Taipei, Bangkok, and Hanoi. Yes, you can see here, Bangkok and Singapore, always hot and humid climate cities. The temperature is around 22 to 23 degrees always. So it's almost similar to inside the building of Tokyo in the winter season. Yes, this is the real fact. Other facts clarified by ourselves is this data. This is a sample data of Singapore office, almost similar to Bangkok. Because of the temperature is quite like a winter season inside office space always. So people's thermal sensation board, it means, do you feel cool, warm, cold, hot? The result is very convincing. People feel slightly cool, especially women say cold, too cold, like that. This is very understanding. But the problem here, when it comes to comfort, people prefer to slightly cool situation. This is totally different from international standards of thermal comfort. But other aspects, when it comes to symptom, it's kind of sick. A lot of people make a sensation about cold sensation on the hand, leg, body, and sometimes feeling some shoulder ache, headache. This is very typical symptom. Too much cool environment. So as a result of this kind of excessive cooling inside the buildings, energy consumption is very actually bad. This is a result of comparison of baseline and actual energy consumption, our target buildings in each cities and each buildings. Mostly the target buildings is certified as like a LEED Gold, Platinum, or local building certification. But some buildings is much more than baseline in actual. So, for example, when it comes to the Platinum, Gold level green building certification, the target level of the energy consumption is less than almost 30% reduction is required from baseline, but actual situation is not like that. So this graph is much more clear to understand a relationship between baseline and actual energy performance in our target buildings in tropic Asia. The blue dot represent non-certified. Orange dot represents gold, and the purple is platinum certification level. So as I mentioned previous graph, despite of the certified buildings, some building is much more than baseline in actual situation. In other problem is, you can see the difference of this building certification doesn't affect actual energy performance so much. So this is very problem, I think. This is because current green building certification is mainly, the target is design performance. Design performance means simulation level. So this is very problem. So I just summarized our research projects in two sectors. Actual status of green building in Asia is like that. The temperature is quite low, and occupants prefer to cooler environment. Maybe you also agree to this situation. But symptom is frequently observed. It's not healthy for people. And energy consumption for air conditioning is quite large. And the problem is green building certification doesn't affect building performance directly, then the operation and maintenance performance check system is needed to realize sustainability of the building. So next, I'd like to talk about possible solution to make it better, this current situation. One of the test case is this building in Thailand, Bangkok. As you may know, this is a EGAT Tour 103, completed 2019, 2 years ago. And this building is certified LEED Platinum, maybe, I think. So one of the characteristic of this building is not facade. Important thing is chilled beam air conditioning system. Maybe the first case of Thailand, this kind of advanced air conditioning system. I don't explain in detail, but the important thing is this air conditioning system realize dehumidification even if the set point temperature is higher. So this is very important point. So this is a very typical situation in the normal office building in Bangkok. I don't clarify the building name for this, but because of the building's management size understanding, we are allowed to change set point from 22 to 23, 24, and 25. And we also do the 26 as like Tokyo building. But when it comes to 26 degrees Celsius set point, office workers started to go home. So this experimental study was quit. So we can just get 23, 24, 25. Then you can see the temperature is going to higher according to set point is increasing. But at the same time, absolute humidity is also suddenly rising up. And it's almost outside of the comfort criteria, ISO standards. So I think maybe this is the reason why people choose lower set point temperature to ensure the dehumidification. This is very mechanical engineering problem, I think, but anyway, this is one of the very important point to reduce energy consumption in the tropic areas office space. So when it comes to EGAT new chilled beam air conditioning system, compared to the conventional air conditioning system, as I explained previous slide, in the conventional air conditioning system, when we change the set point temperature, suddenly the humidity is very bad. But when it comes to chilled beam system, even if the set point temperature is increased, dehumidification is kicked, then maybe people can accept. So this is the result of our questionnaire survey to the office space people. Yellow line shows the result of conventional air conditioning system office buildings in Bangkok. Then the people's percentage of acceptance board for the indoor indoor environment quality is in maximum around 23 degrees Celsius. Yeah, but when it comes to the new building, like a chilled beam system, advanced operated air conditioning system buildings, set point the people's satisfaction is going to be maximum around 25 degrees Celsius. This is our research result of real fact. So there is very big potential to install this kind of advanced air conditioning system I think. So next example is Central Tokyo. This building is YKK 80 building, headquarter of YKK Corporation. YKK is, as you may know, a zipper on your clothes, and the famous other architectural material also. So this building was completed 2015. One of the very important characteristic of this building is facade design itself and the radiant cooling system, entire buildings. This building is mainly using this kind of radiant cooling system for cooling. Of course, there is some air-based air conditioning system also for the dehumidification. So other important characteristic is radiant cooling system itself is very famous in Europe. So in Japan, we also have a lot of radiant cooling system projects in Central Tokyo, but almost a previous radiant cooling system is just import from European system in the Central Tokyo. Then as you may know, European people hate air draft. So normally the radiant cooling system doesn't use any air moving fan for the air conditioning system. But in Japan, previous radiant cooling system project, people sometimes feel some uncomfort because air is always static. So in this project, we try to install this air additional fan system to enhance humans' comfort on the radiant cooling system. Before the construction, we do this kind of mock-up experimental study to the 150 subjects. This is a direct comparison between radiant cooling and slight airflow additional air conditioning system and the conventional air-based air conditioning system. As a result of 150 subjects questionnaire survey, we find out enhanced comfort area, especially just maybe for the Asian peoples, can be accepted if we have additional air diffusion. We can accept around 27 degrees Celsius under the radiant cooling system. So this is this result, I think maybe can be applied for Thailand also, I think. So we are now seeking for the actual case study in Bangkok right now. So next example is facade design. This is a previous project for me also. This building was completed 2005, around that. So one of the very important characteristic of this building is, anyway, building facade. As you can see this animation, this building has almost 100% window to wall ratio, but outside building facade, this building has external shading louver, entire building facade, and this facade is mechanical controlled towards sunlight condition. This design is imagined from traditional building design of Japan, like this. You can see in Kyoto. This is very clear result of how much external shading devices is effective for inside buildings. We conduct a directory comparison between external shading devices and the internal shading devices in this Nikken headquarter buildings. So this is a comparison of infrared image at the same time. In the midsummer of Tokyo, external shading devices inside window surface temperature is around 30, while internal shading devices is more than 36 degrees Celsius. Yeah, almost the visual situation is same, but thermal performance is totally different. The shading device is outside or inside. In this building, we also try to research and develop this kind of automated shading device control system. This system detects direct sunlight. It means the outside climate is cloudy or clear on the day, and they also detect the solar direct, solar position, yeah, solar altitude over the year. Then the system decided to the angle of the shading devices. Almost interval is 1 minute, and if the outside is cloudy, the shading device is open to keep ensuring the view outside, and maximize daylight performance at the same time. So at the same time, this shading devices and the facade system is integrated with lighting system. This is very simple and a very cheap system to utilize daylight and the dimming control lighting system. So this is a result of the numerical simulation by myself. And this result is very clear to understand how much this kind of building facade performance affects energy performance of the building. Horizontal axis represents window to wall ratio. This is simulation. We can see the 0% case study at the same time. The vertical axis represents elemental energy consumption of the office building in the central Tokyo entire year. So we try to focus on the blue dashed line here. This case represents in case of building facades has clear glass, single pane. It means poor performance glasses without daylighting utilization, without shading devices. Yeah, this is very nothing for the sustainable building design and the system. Then the energy consumption is just increased towards window to wall ratio. Maybe this is very reasonable. Yeah. At the same time, we would like to focus on this green dot line case study. Yeah, it means energy consumption is minimum in this case study. Towards the window to wall ratio, you can see the energy consumption is going to decrease because of the daylighting effect. After 40% around window to wall ratio, just a little bit energy consumption is increasing. So this case study represents with lowy grass, multi-layer grasses, high performance grass, and with external shading devices, it's like and with dimming control, and with shading device automation control. It's like a Nikken Sekkei case study. Yeah. So when it comes to this kind of high performance facade buildings, window to wall ratio doesn't affect energy performance anymore. So I think maybe in Thailand and the tropic Asian countries, this kind of facade design and system must be tried, I think. So I showed some case study and the possible solution for towards zero energy building in Asia. I think efficient dehumidification is quite important technology. We should try as soon as possible for the existing building in Thailand also. Air diffuse enhanced comfort and energy efficiency must be also tried, because Asian people's thermal sensation and comfort may be different from Europe or American people, I think. And the facade design and system is also quite important. One of the problem of architectural education is, I think, this point. Students want to just design the glass box for the super high-rise building, but what happened after this design building results, we also have to educate. I would like to finalize my presentation with this my suggestion for the collaboration with you. So we are working for university, so we would like to enhance university collaboration with Asian and Thai university, because we need to collect data much more. Our data number of the level of the data is just several 10 or 30 or 50 level right now, but we need to increase 1,000 level to make it much more convincing. Yeah. So we would like to do the case study also altogether. And I also very keen to do the student workshop to make young students understand how this kind of building performance is important at this moment. And I also very keen to industry government collaboration because even if Japan building sector is quite very slow to realize zero energy building construction right now, because we need to make government action. We need to convince them based on the data-driven strategy. So this is just my suggestion and my idea. So I would like to finalize my presentation, and thank you very much for your attention. And I very hope to collaborate with you and discuss about this kind of matters. Thank you very much.
Thank you very much, Associate Professor Masayuki Ichinose, for telling us about the local factors of urban building performance, especially in tropic Asia. We have learned a lot about energy efficiency and how do we use technology and design to help us deal with the global issue, which is climate change and ขอบคุณนะคะรองศาสตราจารย์ดรมาซายุกิอิชิโนเซะนะคะที่มาให้ข้อมูลพวกเรานะคะเกี่ยวกับปัจจัยต่างๆที่เราควรคำนึงถึงนะคะในการออกแบบนะคะหรือว่าการใช้งานอาคารต่างๆนะคะโดยเฉพาะในเมืองในเขต tropic เอเชียนะคะเอเชียเขตร้อนนั่นเองค่ะและลำดับถัดไปนะคะก็จะเข้าสู่ช่วง exclusive Q&A นะคะเราได้รับเกียรติจากวิทยากรทั้ง 4 ท่านนะคะไม่ว่าจะเป็นทั้ง Professor Michael Siminovich นะคะเราได้รับเกียรติจากดรอโนไทยธนเจริญกิจนะคะจาก Lawrence Berkeley National Laboratory นะคะอีกทั้งค่ะเราก็ยังได้รับเกียรติจาก Associate Professor ดรสุภกิจสุทธิเรืองวงศ์นะคะรวมทั้งล่าสุดเลยค่ะท่านวิทยากรนะคะ Associate Professor Masayuki Ichinose นะคะจาก Tokyo Metropolitan ค่ะ And in the next session there will be an exclusive Q&A. We have collected the questions you have sent us in the chat box and you are always welcome to send us more questions. We will select the questions and ask them for you.In this session, we are lucky to have our 4 distinguished guest speakers who have shared with us their insights and perspectives in the morning session. We have Professor Michael Siminovich from UC Davis. We have Dr. Anothai Thanachareonkit from Lawrence Berkeley National Laboratory. And we have Associate Professor Dr. Supakij Suttiruengwong from Silapakon University. And lastly, we have Associate Professor Masayuki Ichinose from Tokyo Metropolitan University. Thank you for joining us in this Q&A session. The first question I would like to ask Professor Michael Siminovich. It's a question from our audience.The first question is about decarbonization. In your presentation, you have talked a lot about decarbonization when it comes to operational energy used, but the question is, how do we reduce or eliminate the embodied carbon when it comes to embodied energy? So, would you please answer our question, Professor Michael Siminovich?Hello, Professor Michael Siminovich. So there are 2 questions for you in this session. The first one I have asked you about decarbonization. Professor Michael, can you hear me? Can you hear me?Okay, there are some technical problems. We apologize for the inconvenience, and I'm sure that there will be a Q&A session in a minute. Hello, can you hear me, Professor Michael Siminovich? Hello, Michael.Can anyone hear me right now?
Can you hear from my screen?
Yes, I can hear you. Okay. So the first question will be for Professor Michael Siminovich. Okay.Can you hear me now, Professor Michael? Yes? Okay. So the first question from our audience is about decarbonization. So you have talked a lot about operational energy, but what about the embodied energy? How do we reduce the carbon emission when it comes to embodied
energy?So I couldn't hear you.
Oh, you cannot you still can't hear me? What about now? Can you hear me? Professor Michael Siminovich. Can you hear me?
Yes, I can. Thank you.
Okay. Okay, sorry for the inconvenience. So the first question for you is about decarbonization. You have talked about operational energy, but when it comes to embodied energy, how do we reduce carbon emission?
Yeah, that's a really, really great question. One of the things that we've been looking at is a lot of the materials, apparatus, building components, construction materials, a lot of embodied energy. I mean, for example, solar collectors and solar panels. A lot of this there's a lot of embodied energy in a lot of these renewable devices. And so we need to be concerned about that. Also, things like new lighting components, a lot of the new hardware, a lot of the new electronics, the glass, the materials, all have embodied energy. And so we typically calculate these things based on the energy saved, but and the carbon avoided directly from operational energy. But we don't often look at the whole process. I mean, we're starting to think about this now relative to construction materials and looking at low carbon concrete, for example. We need to extend this kind of view, not just from construction materials, but in the devices that we use, the electronics and even in lighting systems, we're starting to look at how do we minimize the amount of waste just in the materials and the carbon that's embodied in that process. So I think we need to extend this embodied energy issue, not just from construction materials, but into actual devices, appliances, much more on recycled components. We're starting to launch an initiative here where we're looking at a cradle to grave kind of concept with appliances. And so we start using appliances to design them to be much more sustainable so that much more of the materials remain in place and we only replace small components of it. For example, in a lighting system, maybe we only need to replace a very small part of it, but we can leave a lot of the embodied energy in place. And so this kind of cradle to grave concept with embodied energy needs to be really extended. So it's a great question and it's a great issue.
And the next question for Professor Michael Siminovich as well. The next question is about how do we know what is the right level to dim the light to balance between energy and security? Can you please answer this question, Professor Michael Siminovich?
Yes.
Thank you.
It's a great question. And so when we first started looking at dynamic or adaptive lighting processes, we were really concerned about the whole safety issue and the idea that if we reduce the lights, is it going to be a safety concern? Are people going to feel less secure in these kinds of environments? And so what we found in our first series of experiments is that we were able to reduce light down to about 50% before people really started to notice. A just noticeable difference for lighting is 15 to 20%. So you can actually dim lights 15 to 20%, and most people won't notice it. And if you ramp lights slowly, you can turn it down to 30, even 40%, and people won't notice. At 50%, they notice. And so I think that there is a real need to balance this kind of safety, security, and energy savings. What we found in our experimental work was that with sensor-based lighting, actually you accentuate the issue of safety and security because people feel a little bit more aware when the light is responsive. Someone enters into a parking lot, someone enters into a corridor, the lights get brighter. And so this actually gives a sense of welcoming or a sense of added attention. And so our studies on campus, when we interviewed students and staff, we found that really, wow, I feel much better the lighting because I see it getting brighter as we get closer. So at first level, 50% we don't see as an issue. And we actually see the potential down the road to accentuate the concept of safety and security by having a more dynamic, a more welcoming kind of opportunity. The second issue was actually running these lights in reduced or 50% mode during periods of vacancy. Actually, the lights last longer. And the big issue with safety and security in municipal lighting is lights burning out early or expiring early or failing. And so while lights that are left on for long periods tend to fail in an earlier mode. So we're really seeing this as an opportunity to extend the life and reduce lamp maintenance issues in municipal lighting applications. And the reports that we're getting back from municipal partners is that they're seeing a lot less failures. And we see this as a really important opportunity for safety. It's really campuses and cities respond more to early failures relative to security and safety than any other issue. So it's a great question. Thank you.
Thank you very much, Professor Michael Simonovich. It's really interesting to learn that actually by having like sensor-based lighting, we are more aware and have more attention, and that adds more security in our life. And the next question is for Dr. Anothai Thanachareonkit from Lawrence Berkeley National Laboratory. You have been telling us a lot about interesting research. Are there any suggestions or recommendations for universities in Thailand or people in Thailand who are interested in future collaboration?
Thank you, and thank you for your interest in Berkeley Lab and the Windows Group. Actually, each year, during the pandemic, Windows Group has welcomed the visiting scholars, students, visitors, PhD students, professors, lecturers who share the same interest in window research to come to work with us, and not only in the window group, also in the other group in our department, or I'm sure even in the lab. Yeah, some of them use our facilities and softwares for their research projects. And I personally went to Berkeley Lab during my study in 2007 and learned about luminance mapping techniques, and also using the Windows Group facilities for my study before joining the lab in 2010. I simply wrote an email to people in the group. I initially was searching read their papers, and I found that okay, this should match my interest, and simply wrote to people in the group and asked directly for their support. And normally people in the group answer the questions and try to help, particularly when the questions are related to our research and technologies or our facility and software. And recently, we have collaborated with several institutions on research projects from many countries and continents. So I'm sure, but first, we want to be sure that we share the same interests and we can help you, that we can support in this collaboration. If you are working on any project and you think that people in our group or our department could support your research, please contact us directly and we can figure out the next step. Thank you.
Thank you very much, Dr. Anothai, for your kind invitation for anyone who are interested in this window research. And I'm sure that there will be a lot who will contact you and your group after this symposium. And the next question would be a question for Associate Professor Dr. Supakij Suttiruengwong from our Thai audience, who are asking about the household biodegradable or bio-based materials and products that you have invented and designed. Are they available in the market? Have you ever put them in the market?
I think this is, thank you very much for this question, because it's interesting in terms of applying a new products or launching new products into the market. In case of Thailand, I think the adoption of the markets is very difficult because you need some regulations and also some, it's very difficult to complete with existing products. So what happened was, in our group, we also work closely with the company. Most of the company, they export these goods and items abroad, for example, to European countries and also Australia, where these countries are well adopted in terms of biodegradable and bio-based materials. So in this case, you can only see some products in Thailand, but very little in terms of standards and also adoption. I would say it takes some time to these transitions to happen. I would say maybe 4 or 5 years from now, we can see more of those adoption. But at the moment, our research normally with the companies, and they export the goods. And for our startup, they are working closely with the farmer, mainly agricultural sectors. So let's see, I think in 2 or 3 years times, we will have a more bio-based and biodegradable products in place and adopt by the many stakeholders. Yeah, thank you.
Thank you very much, Associate Professor Dr. Supakij Suttiruengwong. I'm sure that a lot of us are looking forward to that transition and that trend in Thailand. And the next question is for Professor Masayuki Ichinose from our Thai audience. One of the questions is, since COVID-19 pandemic, people are more concerned about health and the air quality of the indoor air. So what do you think these concerns affect the future trend of energy use in building?
Yes, this is a very important point. And inside Japan, we are very eager to discuss about this matter. But when it comes to the tropic countries building, and especially Thai buildings, from the experience of our on-site survey, actually this ventilation performance is not good. And so because of COVID-19, and the people are now very interested in this air quality issues, it's time to change ventilation air conditioning system at this moment. Especially as I explained in my presentation, dehumidification is quite important for the energy consumption and the people's satisfaction and health at the same time. Maybe we are going to try other case study soon later, and would like to share if we have some results. Yeah, thank you for your question.
Thank you, Professor Masayuki. We also have another question just now for you. So the question is, with the automatic facade system that adapts to the global horizontal radiation with 1 minute interval, has it been implemented in a real project? If it has, how was the feedback from the users? Have they complained about any visual discomfort?
To me? Yeah.
Yes, for you.
This 1 minute interval control system was adopted almost 10 to 20 buildings in central Tokyo already. And one of the problems was initial development system was just 1 minute interval control system. But of course, sometimes outside climate is not like just only cloudy day, just only clear day. Sometimes fluctuate a lot. So as a result, every 1 minute open and close and open and close was happen, and some people, occupants, complain about this. It's something too much for the control. Then after that, we also develop and renovate it to much more learning about outside situation. Is it fluctuation day or very constant or not? And how we concretely say we just set some other parameters to reduce the moving of the shading devices like that. And after that, people's satisfaction was increased. We have such kind of experience. Yeah.
Thank you very much. I would like to take this opportunity to thank all our guest speakers, Professor Michael Siminovich, Dr. Anothai Thanachareonkit, Associate Professor Dr. Supakij Suttiruengwong, and lastly, Associate Professor Masayuki Ichinose for your presentation and your answers. กราบขอบพระคุณค่ะ
Thank you very much.
Thank you. And in the next session, which will be after our lunch break, we will meet 6 more guest speakers. And now it's time for lunch break. We will reassemble at 1 o'clock and listen to more on this symposium theme. และในเวลานี้นะคะเป็นเวลาพักรับประทานอาหารค่ะเราจะกลับมาพบกันใหม่นะคะเวลา 13 นาฬิกานะคะแล้วก็จะมารับฟังการบรรยายจากวิทยากรอีก 6 ท่านค่ะแล้วพบกันใหม่เวลา 13 นาฬิกาค่ะขอบคุณค่ะ
I miss you, tell me what I should do, 'cause all I think about is you, and only you. If I could turn back the time, I promise that we'll be alright, just you and I, together until we die. I just want you by my side. I promise that I hold you tight. Just you and I. Together we will be fine. Remember when I say forever? Baby, I really mean it like forever. Can we be together? I swear if you be here, share me all your worries. My ear will love to hear all the years that I spent with you. Swear to God that I don't wanna lose.